Hi, my name is Emma Glasser. I'm a senior studying material science and environmental science in the Viper program. And today I'm going to talk to you about an incredibly important material. It's the second most consumed material on Earth after water. We're talking 30 billion tons are produced annually. It's responsible for 8% of global CO2 emissions, and it's the third largest industrial energy consumer. It's right beneath our feet and quite literally the foundation of industrialized society. So today we're talking about concrete. Concrete is everywhere, from sidewalks, bridges, the foundation of every building, and the building structure themselves. So we've established that concrete is incredibly important, but also incredibly energy and carbon intensive. So if we want to stabilize climate and a just and livable future, we need to decarbonize concrete. I'm excited to talk to you about a project I've been working on for the past 7 months with a team of 5 Penn engineers to develop a climate conscious concrete. And before I get into any details, I want to thank the people who've helped me on this project, my teammates, Yane, Leslie, Kim, and Sahana, our project advisor, Dr. Yang, the MSc lab manager, Steve Sedgwick, and then Dr. Kunhao Yu, Dr. San, and Dr. Barsam for their advice and guidance. Thank you all. So I want to talk about why concrete is so ubiquitous. And it really comes down to the fact that it's strong and cheap. So here we have an Ashby plot, which is a common plot that we use in material science to determine which material suits a given application. And so I've plotted here compressive strength versus price. And compressive strength is how much weight or load you can put on a material before it breaks. And we're interested in compressive strength for concrete because, as it turns out, this is the property that it's strongest at. It's why we use it in foundations, in columns, in sidewalks, applications where we need a material that doesn't crack under pressure. So if you look at the plot, you can see that concrete is the strongest, cheapest material. If we wanted to use plywood, we could have maybe 1.5 times the strength, but at 5 times the cost. And concrete is strong enough for most applications. And what we've ended up doing is adding in steel rebar if we want it to be even stronger. And the reason why concrete is just so inexpensive is because it's made of incredibly abundant materials, which I'll get into later. And so it's because it's the strongest, cheapest material that we see it everywhere in just about everything. That's how we get 8% of global CO2 emissions. So the global concrete market reached $617 billion in 2020. And because of climate concerns, there's a growing green concrete market that reached $24 billion in 2020. And it's expected to double in the next 6 years. So my team has been trying to use our understanding of material science to design a climate conscious concrete. And in order to understand how we've been approaching this problem, it's important that we understand the fundamental building blocks of concrete. So what is concrete? Concrete consists of cement, water, and aggregate. And cement is the glue that holds the aggregate or sand and stones all together. And although cement only makes up around 12% of concrete by volume, it's almost exclusively responsible for the emissions that come from concrete. So what is cement and where do cement emissions originate? So cement is composed of many different materials. We have alumina, magnesia, lime, silica, and iron oxide. But to get here, we have to do a whole process. So the raw materials include limestone, gypsum, shale, and iron ore. And the main one by far is limestone. So limestone is found on almost every corner of the world, and it's incredibly abundant. And the way that cement is made is we quarry limestone and we combine it with these other raw materials, and then we put it in a kiln, and we heat these raw materials up to 1500 degrees Celsius or over 2500 degrees Fahrenheit until they're quite literally glowing red. And this is an image of a rotary kiln of cement. So it rotates, and this is what it looks like. And it's in this process where 90% of the emissions from cement come from. 50% are from the reaction where it's called calcination, and the calcium carbonate or limestone turns to calcium oxide, and in the process, carbon dioxide is released. And the 40% is from the exorbitant amount of energy we need to create this much heat. And so the other 10% is from the excavation, transportation, grinding, and mixing processes. So the industry standard cement is called Portland cement, and the most common is called ordinary Portland cement, which is commonly referred to as OPC, which I'll talk about from here on out. So we asked ourselves, is there a way that we can calcine at a lower temperature or avoid calcination altogether? So in the basement of LRSM, the Laboratory for Research on the Structure of Matter, right down the road, we made ourselves a small but mighty cement and concrete factory. And all of these images are samples that we've made ourselves in the lab. And so we've been approaching this problem by developing two different alternative cement formulations. One, it uses uncalcined limestone. So we're skipping this calcination process altogether and instead encouraging the reaction through the addition of bases. And this type of cement is called alkali activated, and it has the potential to reduce cement's emissions by up to 90%. We're basing our formulations off of a team at Drexel that has made uncalcined cement with strengths greater than OPC. And unfortunately, we have had not such success in the lab, and we're still working to hopefully crack this formula. The other approach that we've been using is using eggshells to create cement. So we've been collecting eggshells in our homes, bringing them to the lab, grinding them, calcining them, and turning them into concrete. And so we are calcining the eggshells, but at a significantly lower temperature, only around 900 degrees Celsius. And this has allowed us to we've used this cement to replace OPC up to 45% with up to 40% emissions reductions. And we've also been able to reach strengths above just OPC alone. So this is really how we've been approaching it. And the last thing I want to mention is one more avenue to reduce emissions is through 3D printing. So instead of just pouring concrete, we can actually, there are companies that are using large-scale 3D printers to minimize materials and energy use and maintain the same level of structural strength and stability. And so we have tried out our extrusion of our cement, and you can see it's working pretty well, and we're gonna do some 3D printing next week. So that's how me and my team have been working to create the climate conscious concrete of the future. Thank you for listening.